In this lesson, we're going to focus our attention on understanding appropriate components that are related to analyzing the memory hierarchy of a system and systems and networks. And so you want to keep in mind that if you recall, in our page memory systems, we have our instruction fetch stage. And typically this requires 2 memory accesses for every instruction. Access for PTE as well as access for the instruction. So what can we do in order to improve this? We could try increasing the cycle time, but that would mean that we would take 2 cycles in the instruction fetch stage as well. Either one of these options aren't ideal. And so we have to think about ways in which we can improve this. Let's consider that we utilize the TLB in order to allow for this to occur with only 1 memory access. And so that's from the PC to the TLB to memory. So that's a better option. But let's kind of consider the timing mechanisms that are involved in this approach to analyzing the speed. Typically, what's the CPU clock cycle speed? It's going to be 1 nanosecond. So what's the memory access time? 100 nanoseconds. So that's roughly a ratio of representative of 100 to 1. So when we go back to our pipeline with a 100 to 1 ratio, what happens in the IF stage on a memory fetch? That'll be 99 bubbles for every instruction. So in a fully working program, that's not a necessarily sustainable approach that we want to take. So let's consider what exactly do we have with our register files and our translation look-aside buffer. They're kind of memories, right? So why are they not a problem? Well, you want to consider that the TLB plus the register file is going to use SRAM or static RAM technology. And so with this reason, we can consider this virtue of it being that speed is easily available. And so SRAM has a better access time than making use of memory, which utilizes dynamic random access memory. And so let's consider how each of these are implemented. With SRAM, we have 6 transistors per cell. So that means that it's going to be faster, but a little bit bulkier. With DRAM, we have 1 transistor per cell. And so that means it's going to be slower and a little bit denser. And so basically this means that we can have size or speed, but not both. And this also means that memory access cannot be part of the CPU clock cycle time. So what makes the principle of a TLB work? We have the consideration of locality. And when we talk about locality, we're talking in terms of sequentiality. When we say the sequentiality of instructions in the program, as well as the sequentiality of the data structures like arrays and struts. So you want to consider that recent translations are stashed away in memory page tables into high-speed hardware. This allows for subsequent translations to become faster, so there's no need to go to memory for most PTEs. So what if we apply that same principle to the data and instructions that we need? In this case, we want to focus on the principle of locality with regards to the instructions as well as the data. And we want to consider spatial locality, and this is going to be the probability of the program needing to access adjacent memory locations. So that would be instructions from I3 to I minus 3 to I minus 2 to I plus 1 minus 1 to I plus 1 and so forth. And so this is going to be helpful when we have data in arrays or records that are occupying contiguous spaces in memory. Now, we also want to consider what might happen if we take into account with temporal locality. And when we talk about temporal locality, we're referring to the probability that our program is going to be accessing the same memory location that's currently stored in the future. And so considering this allows for us to have a more a detailed way to approximate or compute if we're going to be able to access data in memory at a quicker rate. So how can we put these two ideas together where we're considering locality? We want it to be small and fast, or it could be large and slow when we're thinking about the need to access data that is going to be used for our applications. Well, this is where the concept of a cache comes into play. And so if we take into consideration, the TLB is a special instance of caching of addresses. And so let's understand how this model might look. Essentially what we have here is we'll have a CPU, and in between the CPU and main memory, we'll have a cache. And the cache allows for the CPU to first look into it to see if the data that we need is stored there from main memory. If the data is not present, then what we need to do is retrieve it from main memory. And so this allows for the CPU to request the needed data from main memory and store it into the cache for reuse. And as we previously said, the cache is going to be our small and fast, easy to access memory component, and main memory is going to be large and slow. And so taking these into consideration, we'll need to understand how we can utilize both spatial locality as well as temporal locality. And so a few buzzwords to consider for our terminology moving forward is we're going to talk about hit. And when we say a hit, we're referring to the CPU being able to find the contents of the memory address in the cache. So if we can find the contents in the cache, that saves us a trip to requiring to pull it from main memory. And so we also have a hit ratio, H, and that is going to be the probability that we're able to successfully pull the data from the cache for the CPU. A miss refers to if a CPU fails to find the data that it needs in the cache. And so if a miss occurs, then the data gets pulled into main memory and mapped to the cache. And so the miss rate M is referring to the probability of missing data in the cache. And it's going to be equal to 1 minus H. And so we also have a miss penalty as well. And with the miss penalty, we're considering the time associated with servicing a miss for a particular level of the memory hierarchy. We have, and to compute the effective memory access time, we want to consider the time to the T sub C, which is going to be our time to access the cache, plus T of M, which was our time to access main memory, times our memory, our miss penalty, or miss rate, I'm sorry. And so let's kind of understand the way that a cache is laid out in a system. So typically at the top, we'll have our appropriate CPU with the appropriate registers for access. That's always going to be the first component on every memory access. And then we'll have the second component is going to be the number of the registers are going to be used for this component. And then we'll have our L1 cache. And so the L1 cache is going to be typically a little bit smaller than the other levels of cache. The closer it is to the CPU, the smaller the component will likely be. And so L1 cache allows for the quickest access, but it can only store a small amount of data. You can then also access the L2 cache. And the L2 cache is going to be slightly larger than the L1 cache. And then the L1 cache and L2 cache are going to be represented on the chip. The L3 cache is going to be a lot larger than the L1 and L2 cache, typically at least the size of L1 and L2 combined, but it's so large that it's typically placed off chip. And so then we also have our main memory component and other storage mechanisms such as virtual memory. And so keeping these into mind, when we're accessing components from the registers in our caches, we're considering mechanisms that are hardware oriented. And then also working with main memory and virtual memory, those are going to be software based components. And so if we want to calculate our effective memory access time, then it's going to be the time to access the cache, as well as the miss ratio times the memory access time. And so let's kind of consider an example. Let's say for a given system, we have a L1 cache, which a hit ratio of 95% and a time of 2 nanoseconds. L2 cache has a hit ratio of 0.8 and an access time of 10 nanoseconds. And then for main memory, we have a time of 100 nanoseconds. So let's consider how we can access the effective access time for each level of memory. And so we consider that for accessing L1 cache, we'll consider the time plus the miss ratio, which is going to be 1 minus the hit rate. And so that would be 0.05 times the effective access time for L2. And that's computed in the same manner. We substitute in the access time as well as the miss ratio times the access time of our third component, in this case, main memory, is going to be 100 nanoseconds. And so our effective access time is going to be 3.5 nanoseconds for EMAT sub 1. And so we have various ways in which caches can be organized, and these include direct mapped, fully associative, and set associative. And so we'll get into a little bit more detail about each one of these organizations. With direct map, it essentially means that a cache block can only go in one spot in the cache. And this makes a cache block very easy to find, but it's not very flexible about where to put the blocks. So it's very restrictive in that manner. And then on the other way, we have set associative and fully associative. And a set associative is going to place each set in a specific size blocks, whether it's 4 blocks or 2 blocks, to determine if you have a 4-block set, then that's going to result in fewer sets. And so that's going to mean fewer index bits that are needed. We also have a fully associative approach, which means that there's no index needed and a cache block can go anywhere in the cache. The caveat with this is it means that every tag has to be compared when we want to find a block in the cache. So let's first focus our attention on understanding direct map cache. And so in a direct map cache, we have a one-to-one correspondence between a memory location and a cache location. So when we're given a memory address, we know that there is exactly one place to put its contents in the cache. So with direct mapping is pretty straightforward in that we have a memory with 16 words and a cache with 8 words. And so we consider that there are different types of misses that can occur. Compulsory misses are going to occur essentially if our first go around, when we first try to access data, because data is not stored. So the first instructions will always result in a cache miss. We can also have capacity misses when the cache is full. We can have conflict misses when a block is vying for space in a full set in the cache. Compulsory misses are always going to be larger than capacity, which is always going to be larger than conflict misses. So let's consider an initial example. In this example, let's say that we have appropriate memory references that occur in the following order: 0, 1, 2, 3, 1, 3, 0, 8, 0, 9, and 10. Initially, if the cache block is for the first instruction, what we're going to get is that these are always going to be compulsory misses. The first time data is accessed or pulled, it is going to result in a miss. So 0 is going to result in a miss because it's the first time. 1 is going to result in a miss because it's the first time. 2 and 3. And so each time it's missed, it gets pulled from memory and then it's stored into the appropriate cache location. So now when we go and we access one 3, and 0 again, this is going to result in hits. But when we go to our next instruction of 8, this is going to result in a miss. And so now 8 will get placed into the cache. And so what we do is, to calculate where it's placed, we do the 8 modulo 8. And so it gets placed in the cache location of 0. And so now this, when we go to 0 again, this becomes a conflict missed, because it can only be stored in location 0. So we have a miss again for 0, and it gets put into the cache. And now we pull 9. This will be a miss, a compulsory miss, because this is the first time that we're pulling data for 9. And so we want to consider, if we have a 4-bit memory address, 3 bits are representative of the index. And so we would need to do 9 mod 8 to determine the address that 9 will be stored in our cache, and it's going to go into location 1. And so the memory addresses, the index will always be the memory address mod the cache size, and our cache size here is 8. So how do we disambiguate data? This means we need to know whether it refers to, this means that we need to know if the information that we have in the cache is distinguishable to multiple memory addresses. And so what we'll need to do is we're going to incorporate a field called a tag. And so we'll have a 3-bit index, and then the remaining bit is going to determine if the cache data is for memory addresses 0 or 8. For 0, and then 1 or 9, depending on the memory location. And so how do we know if the data is valid? The tag can be used for us to disambiguate whether the data is in the memory location currently in the cache, but it doesn't necessarily help in knowing if the entry is going to be valid. So at power up for a cache, it could contain initial garbage. So the tags can help to disambiguate the data, but it doesn't necessarily provide for data validation. So in order to build on this, what we'll need to also include is a valid bit. And so now we have metadata that is represented from a valid bit as well as a tag, and then we have our real data as well. So from a hardware perspective, let's consider that we have our block of data, and we have 1K entries. What are going to be the sizes needed for our cache index as well as our cache tag? So we know that the log of the cache size is going to equal the log base 10 of the cache size is going to equal a 10-bit index. And so this means that if we do 32 minus 10, then we're going to have a 22-bit tag. So the cache index is going to be from 0 to 9, and the cache tag is 10 to 31. And so our bus for accessing from the cache index is going to be a size 10. And for the cache tag, it's going to be a 22, which means for our comparator for the tag is going to be that same size. For the valid bit, it's just going to need to be able to transfer 1 bit, and the data is going to be 32. And so let's interpret how the memory addresses are stored. And so with the 32 that we need to use from data to the CPU, you want to consider that the cache data is going to be the width of the memory to CPU bus. So each index is going to be the memory address mod cache size. And so if memory address 8, cache size of 8, then the index is going to be 0. If the memory address of 0, modulo of 8, the index is 0. And the number of tag bits is going to be equal to the memory address size minus the cache index size. So a good question is, why not use it the other way around, where we use the low bits for the cache tag? So if we consider index first, that is 1 bit, and then the tag last. In our first example, access location 0, and then we go to access location 1, and then we go to access location 2, and then we go to access location 3. This results in a lower occupancy, so we have a loss of spatial locality. And so let's consider the design of a direct map cache for a memory system. You want to keep in mind that we want to assume the CPU will generate a 32-bit byte addressable memory address, and each memory word contains 4 bytes. A memory access brings in a full word into the cache, and the direct map cache is 64 kilobytes in size. So this means with each cache entry containing 1 word of data. And we want to compute the additional storage space needed for the valid bits and the tag fields of the cache. So we want to consider with real data, 64K divided by 4 is going to be equal to 2 to the 14th rows in the cache. And so we want to consider only word addresses for the lookup. So in this case, we'll have our cache tag being 16 bytes, cache index 14, and our bytes offset being 2. And so when we store it in cache here, we're going to store our data in 32 bits, with our tag being 32 to 48, so 16 bits, and then our valid bit just being 1. So this takes a total of 49 bits. 50 bits. And so what this means is that we can calculate that we're going to need 2 to the 14 times 17 additional bits additional to use. And so with this in the consideration, we can see or depict how a memory address is interpreted for a single cache block. And so we can have our cache tag that will go to our comparator to determine where it's located in the cache. We have our cache index, and then we also have our appropriate data to the CPU that can be utilized. And so a question to recap: a direct map cache has a many-to-one mapping between a memory location and a cache location, allows a memory location to be in cache wherever there is space in the cache. C is so-called because there is a directory associated with the contents of the cache. Or D is usually much smaller than any other type of cache organization. And so in this example, what we shown from our previous example, that it's going to represent a many-to-one mapping between the memory location and a cache location.